Hello guys, welcome to podcast. Hope you are doing good. And today in this session, we'll discuss the topic quantization, and we'll also do the implementation part and see how quantization is helpful and what are the drawbacks and also the use cases. So let's start. Now, starting with the definition, okay, we'll actually see what is quantization. What is quantization? Now, the first point is it reduces the precision of it. Okay, so it reduces reduces the precision of weight or the activation, you can say activation from float 32 to int8 or float 16. So what actually we are trying to do here, we are trying to, it helps basically, it helps make models smaller and faster. Now it is especially useful for LLMs and edge devices. Now we'll see the benefit. Now the first benefit is its smaller size. So whenever the model will be of smaller size, what will happen? We will require less storage. We will require less storage. Second is faster inference, right? That means we'll get the result fast and we can test the model more in what we can say in less time, and especially when we are on CPU, especially on CPU. Next is lower RAM usage or memory usage, lower memory usage. That is, we can say it is RAM efficient. It is RAM efficient. These are the benefits. Now we'll see the drawback. What are the drawbacks? Okay. The first drawback is accuracy is drop slightly. So slight accuracy drop is there of the model which we are dealing with. Next is some hardware may not support all quantized drops. Okay. Some hardware may not support all quantized operation. And the last is not all models quantize well. Not all models quantize well. Okay. I will see the use cases. First of all, the chatbots on mobile app. Uh, then you want to run LLMs on edge devices. So running LLM on edge devices. And third, we use faster inference in production. Faster inference in production. These are the use cases, drawback, benefits, and now first of all, we'll start with the implementation part. You will need to install required library. Step one will be install required library. We will install transformers library for Hugging Face model, right? Hugging Face model. Then we will install Torch with PyTorch, and when you install, quantization tool. Okay, quantization tool. Mention tape install, transformer, then tensor flow, and torch, and accelerate, and then bits and bytes. Wait, huh? Now the next step after installing, we'll load a small LLM like digital bot. For loading the small LLM, we'll require from transformer, we'll import auto tokenizer. Then we'll require auto model for classification, sequence classification. Basically, we are loading model and tokenizer. Then we'll import torch, that is the main library for PyTorch, main library for PyTorch. We'll then load the pretend digital model. So load pretend digital model for sentiment analysis. Load pretend digital model for sentiment analysis, and we'll mention the model ID. So mention model ID, that is the digital bot date and case, fine tune, and then set the to English. Now you can directly get this ID from the Hugging Face. Just mention the model name, insert, just mention this bot, and you will find this. Now what is this? This is a sentiment classifier model. So mention this sentiment classifier. Okay, I'll run this. Then we'll load tokenizer. That is now tokenizer is used for what? Load tokenizer. Load tokenizer. So we are converting token text to token, and we'll also load model. We'll load tokenizer and model for inference. Definition the tokenizer equal to auto tokenizer and from retrained, and I'll mention the model name, that is the model ID, and for model I'll mention auto model for sequence classification from retrained and model name, so that is the model ID. Okay. After that we will prepare an input sentence. So prepare an input sentence. So my text would be, oh, this movie is surprisingly, surprisingly good. Okay. So this is my text, and then I'll mention the input is equal to tokenizer. I'll mention the text. I'll mention the return tensor equal to pt. So it will return a PyTorch tensor. It will convert text to PyTorch sensor. PyTorch sensor. Run this. Now we have prepared the input sentence. Now we'll run inference for quantization. We'll run inference before quantization. So we can compare the model output before and after. So we'll use with torque, torque. This will basically disable the gradients for disable gradient for inference. To mention original output, and alpha model and input. So it will run the model, and get output. And then I'll print original model output. Okay. Original model output, output. Yes, and torque, softmax, softmax animation, original output, dot log it animation the damage one. It will basically print the probability. Probability. Okay, you got the probability. Now third step, we will apply the dynamic quantization. Next step is we will apply dynamic dynamic quantization. From dot quantization code, the quantize dynamic. So this will basically import the PyTorch quantization function. Quantization function. When we will apply quantization to linear layer, next step is we will apply the quantization to linear layer using integrate procedure. So then it's a quantize model equal to quantize dynamic. Okay, quantize dynamic, and I'll mention the parameter. First of all, I'll mention the model. Now this is my original model. Okay, original model. My original model. Next is I'll mention dot 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 linear. Okay, so this will basically only quantize linear layer. Linear layer. After that, we'll mention the data equal to dot dot q int 8. Okay. This is quantize to int 8. Quantize to int 8. Then we'll run inference on the quantized model. Okay. Next step is run inference on quantized model with dot say quantized output quantized output equal to quantized model as model, and I'll pass the input. Okay. Then I will print the output, mention quantized model output or dot softmax mention output output, and then log it. Initial dimension as 1. And this I got the probabilities of the quantized model, right? Here I got the original model output, and here I got the quantized model output probability. Now we'll compare the model sizes. Okay. Our step 4 is to compare the model sizes. For that we'll import OS and we'll import temp file. Then we'll save model to temporary directory for site comparison. We'll save model to temporary directory for size comparison. Okay. I mentioned that P32 directory equal to temp file dot mk, and I'll mention int8 equal to temp file. Now we'll save the model. So model dot save retrain, and I'll mention fp32 directory. Okay, which will save the original model, and then I will save the quantized model. Okay, I will save it. Int8, which will save the quantized model. Then we will check the next tab. We will check the size on the size of this. For that we will import pathlib, get a function name get directory size. I'll mention the path. I'll return route that size for in pathlib dot path. Mention the path. Will someone the file sizes. And at last we'll print the model sizes in megabyte. Okay. Last we'll print model sizes in megabyte. I'll print here SP32 model size. We can browse. Get directory size, the function. I'll mention SP32. Click. Then I'll print for the quantized model int8 quantized model size, mention around, get the size, and rate 8, comma 2. We're getting the error for this line. So this was error because we could not, what we can say, save the context model using the PyTorch native save. So we replaced this by torch.save and we got the result by running this test. So as you can see, the 32-bit model was 267 MB, and in case of we converted into int 8, we reduce the model size drastically to 138.72. So in this way, we can use quantization to reduce the model size and get faster inference. Now we'll see the code to compare the output. Compare the output. For that, we'll import torch.nl or functional as that. Then we'll compute the softmax probability. Compute softmax probability. Probability. We'll see the original probability. Null to f dot softmax. I'll mention the original output and log it. Make integration equal to 1. Quantized out probability dot softmax. Quantized out dot log it. Dimension equal to. Then we'll print the probability. Print probability. That means print original modulus probability. Then I'll print quantized model. Quantized model probability. One. Okay. Now we'll compute the absolute difference. Compute absolute difference. Or not absolute of minus of. Then we'll print that the absolute difference in probability. Absolute difference in probabilities. Then we'll see the cosine similarity of log it. Log it. That is closer to 1 equal to more similar. Closer to 1. It will be more similar. And then we will print it at the cosine similarity between log it way to get perfect. So, well, f dot cosine similarity. I'll mention the original output dot log it and quantize output dot log it of similarity. So we got the cosine similarity between log it as it is closer to one, so it is more similar. So there is no natural any difference between the two models or the output from the two models, which is for the original output and the quantized output. So even though the model size has decreased, there is not much difference in the output from the two different models. And so we have naturally reduced the size. We have increased the RAM efficiency of our what we can say of our system by loading the smaller model. We have got the much good inference rate by reducing the size of the model. So if the cosine similarity is greater than 0.9, we got it as 1. So its outputs are almost identical. Now if differences are small, quantization preserved behavior will. There is a large drop. You can try other techniques like that and or calibrated intake. So this is the quantization, and we have seen the implementation how we can convert the 432 model of the digital board to the Intel model, 8-bit model of same model, that is the digital board, and we reduce the size by the model. Previously it was 267 MB for the 32-bit, and we reduced it to 138 MB. So quite of decreasing the size, our model output is same, and that is the good indication that quantization is good here using the smaller model. It is not applicable for all models, and we have not seen the accuracy drop here much, and we got the smaller size, so the less storage problem. So there will be less storage, and we got the faster inference. Basically, we are working on current CPU and low memory rate usage, that is the RAM efficient. So in this way, you can quantize the models, and I hope you guys understood, and you can practice this on your Google Colab. And I'll meet you in our next session with the new topic. Till then, take care. Bye.